truly mind-bending. Electron spin.
It's one of those concepts in physics that just grabs you.
You guys sent a ton of sources our way, so it's clear you want to go way beyond just the surface level stuff.
Right, like what is spin really and why should we care?
You got it. We'll unpack all that and more. And trust me, this stuff has huge implications.
Absolutely. We're talking about everything from how magnets work to potentially revolutionary technologies.
Okay, so first things first. When we hear spin, it's easy to picture, I don't know, a tiny electron just spinning around like a planet, right?
Yeah, I think we all have that initial image.
But our sources are pretty clear. That's not really what's going on at the quantum level.
It's definitely more complicated, but also way more interesting. In quantum mechanics, spin is a fundamental property of a particle, like its mass or charge.
Okay, so not a spinning ball, but what does it mean for this property to be quantized, which is a word that pops up a lot in our sources?
Good question. It means that spin can only take on specific discrete values. It's not a continuous spectrum. Think of it like a staircase. You can only step on certain steps.
You can't just hover in between.
Exactly. And for electrons, this spin quantum number is always 12, which leads to the idea of spin up, positive 12, and spin down, negative 12.
Got it. So it can be one or the other, but nothing in between. Like a coin flip heads or tails.
Exactly. And this seemingly simple concept has huge consequences because it turns out this spin is connected to magnetism.
Wait, hold on. So we're going from subatomic particles to, like, magnets on my fridge? How does that happen?
Well, you can think of each electron with its spin acting like a tiny, tiny magnet itself.
Oh, okay.
And when you've got tons of these electrons in a material, how their spins align with each other, or don't, determines the material's overall magnetic behavior.
So if all the spins are pointing the same way, that's what makes a material magnetic, like a fridge magnet.
That's the idea behind ferromagnetism, like in iron. But that's not the only possibility. Sometimes the electron spins are randomly oriented, and you get paramagnetism.
Paramagnetism.
They are weakly attracted to a magnetic field, but not as strongly as ferromagnets. And then you've got materials where the electron spins pair up in opposite directions, canceling each other out, and those are diamagnetic. They're actually weakly repelled by magnets.
Wow, so we've got this whole hidden world of spin interactions happening all around us, and it explains why magnets stick to the fridge or why some materials aren't magnetic at all. But going back to the atom itself, there's got to be more going on than just the electron's spin, right?
Absolutely. The electron spin is just one piece of the puzzle. We also have to consider the nucleus of the atom, which is made up of protons and neutrons.
Okay.
And guess what? They have spin too.
So it's like a whole family of spinning particles in there.
Right. And to make things even more complex, the electrons aren't just sitting still. They're also orbiting the nucleus, which adds another layer of angular momentum to the mix.
Wait, so we've got the electrons spin, the spins of the protons and neutrons, and now the electrons' movement around the nucleus. It's a lot to keep track of.
It definitely gets complex fast. But all of these spins and motions influence how atoms interact with each other and with external fields.
This is starting to sound like chemistry, like how atoms bond together to form molecules and all that.
You're right on the money. And there's this fundamental rule in quantum mechanics called the Pauli exclusion principle, which plays a huge role in all this.
Okay, I vaguely remember that one from school. Something about electrons not being able to be in the same state at the same time.
Exactly. It says no two electrons in an atom can have the same set of quantum numbers. It's like every electron needs its own unique ID card. And since spin is one of those quantum numbers,
it limits how many electrons can be in the same place.
Exactly. Each orbital in an atom can hold a maximum of 2 electrons, one with spin up and one with spin down.
Oh, I get it. Like there's only room for 2 in each of those electron apartments around the nucleus.
Great analogy. And because of this rule, electrons are forced to occupy different energy levels within an atom, creating a specific electronic structure for each element.
So the Pauli exclusion principle is like the traffic cop of the atomic world, making sure all those electrons stay in their designated lanes.
It's a perfect way to put it. And believe it or not, this is basically the foundation of chemistry. The arrangement of electrons, dictated by the Pauli exclusion principle, determines how atoms bond with each other, forming all the molecules and materials we see around us.
All right, so to recap, we've got these tiny particles, their spin, their combined angular momentum, and this rule about them not crowding each other out. Pretty mind-blowing stuff, but I have a feeling we're just scratching the surface here, right?
Oh, absolutely. This is just the beginning. We haven't even touched on how scientists are harnessing spin in amazing technologies, or how it's helping us understand the universe at a fundamental level.
Okay, I'm already hooked. Okay, so where do we go from here? What else can we learn about electron spin?
Well, get ready for things to get even weirder, because next up we're talking about something called spin liquids.
Spin liquids? What in the world is that? Does that even exist?
Oh, they're very real, and they're a fascinating state of matter. Imagine a material where the spins of the electrons just can't seem to settle down even at super low
They
temperatures.
just keep on spinning.
They're in constant motion, this crazy dance of spins that never quite forms a neat and ordered pattern, and that leads to some really unusual and exciting properties.
Okay, I'm listening. What makes these spin liquids so special?
For one thing, they challenge our usual ideas about magnetism and order. They exhibit something called fractionalized excitations. It's almost like splitting an electron's charge and spin into separate entities.
Wait, so you can pull those apart?
Not literally, but it's as if these bizarre particles called spin-ons can exist, carrying spin but no charge. It's one of the things that makes spin liquids so intriguing to physicists.
Okay, my brain is definitely starting to hurt, but it's a good kind of hurt. Our sources mention some other exotic things like topological insulators and superconductors. Do those have anything to do with these spin liquids?
They do. It all falls under this broader umbrella of topological phases of matter. In these materials, the properties aren't just determined by what's happening at the atomic level, but by the overall shape and structure of the material, its topology.
So it's kind of like how a donut and a coffee mug are topologically the same because they both have one hole.
Exactly. Now imagine a material that acts as an insulator in its bulk, meaning electrons can't flow easily through it, but on its surface it becomes a conductor.
That's strange. So electrons can move freely on the surface, but not inside. How is that even possible?
It's because of these special surface states that arise due to the material's topology. And here's where spin comes in again. In these surface states, the electron's spin is locked to its direction of motion.
So the direction the electron is spinning determines which way it can move.
It's called spin momentum locking. And it makes these surface states extremely robust, meaning they're less affected by scattering, which is a big deal for electronics.
Because scattering leads to energy loss.
Right, so topological insulators could potentially lead to way more efficient electronics in the future.
Now, what about topological superconductors? They sound even more sci-fi than topological insulators.
They are pretty amazing. These materials can host these elusive particles called Majorana fermions, usually at their edges or in vortices.
Majorana fermions, those sound familiar. I think we talked about those earlier.
We did. These are particles that are their own antiparticles, which is mind-boggling on its own. And they have the potential to revolutionize quantum computing.
How so?
One of the biggest challenges with quantum computers is that they are super sensitive to any kind of disturbance or noise, which can lead to errors in calculations. But these Majorana fermions, because of their unique properties, could hold the key to building fault-tolerant quantum computers.
Fault-tolerant meaning they would make fewer mistakes.
Exactly. Their quantum states are much more stable and less prone to errors.
That sounds incredibly powerful. So we're talking about harnessing these weird, almost mythical particles to create the next generation of quantum computers.
It's a very active area of research, but the weirdness doesn't stop there. Our sources also describe something called skyrmions.
Skyrmions.
Think of them as tiny magnetic whirlpools, these swirling patterns of electron spins that are extremely stable, and we can move them around using electric currents.
So we can use them to store information.
That's the idea. They could potentially revolutionize data storage devices, making them much more compact and energy efficient.
Okay, so we've got spin liquids, topological insulators, topological superconductors, and now skyrmions. It's clear that spin is way more than just a simple property of electrons.
Right. And we haven't even talked about its role in our understanding of the universe at the most fundamental level, which goes way beyond just condensed matter physics.
Oh, wow, there's more. So spin is not just a microscale thing.
Not at all. It plays a huge role in cosmology and our quest to understand the fundamental laws of physics.
Okay, I'm ready to hear about the cosmic side of electron spin.
It's pretty amazing how we started with these tiny particles, and now we're going to be talking about the universe as a whole.
I know, right? It's mind-blowing. So where do we even begin? What are some of the big questions that scientists are trying to answer when it comes to spin and the universe?
Well, one of the biggest mysteries in all of physics is how to reconcile quantum mechanics with general relativity.
Yeah, one describes the world of very small, and the other describes gravity in the universe at large scales.
Exactly. And there are some really intriguing theories out there that try to bridge that gap.
Yeah, our sources talk about some pretty wild stuff, like supersymmetry and string theory.
Those are definitely two of the leading contenders, and spin plays a key role in both of them. Take supersymmetry, or SUSY for short. It proposes this really deep connection between matter particles, like electrons, and force-carrying particles, like photons.
Okay, remind me what the difference is between those two again.
Well, matter particles, or fermions, are the stuff that makes up, well, matter. They obey the Pauli exclusion principle like we talked about before. And then you have force-carrying particles, or bosons, which are responsible for the fundamental forces of nature.
Right, right. So SUSY says there's a connection between those two type of particles?
Yeah. SUSY says that for every known fermion, there's a corresponding boson, its superpartner, and vice versa. It's like there's this mirror world of particles.
So there could be a whole bunch of particles out there that we haven't even discovered yet.
That's right, and physicists are actively searching for them at places like the Large Hadron Collider. Now, what's really cool is that Susie suggests that spin is even more fundamental than we currently understand.
Okay, how so?
Well, think about it. The difference between a fermion and a boson comes down to its spin. But if Susie is right, that distinction might not be as clear-cut as we once thought. It suggests that there's this deeper underlying symmetry in the universe, with spin at its heart.
Whoa, that's pretty profound. Like spin is woven into the very fabric of the universe.
And then there's string theory. This one says that the fundamental building blocks of the universe aren't point-like particles, but these tiny vibrating strings.
Yeah, I remember hearing about that. It's like everything is made up of tiny little vibrating rubber bands.
That's a good way to visualize it. And the different ways these strings vibrate correspond to different particles with different properties, including spin.
So spin isn't just an inherent property of a particle. It depends on how these fundamental strings are vibrating.
Exactly. And according to string theory, these strings are what make up space and time itself. So in a way, spin is built into the very structure of reality.
It's like a cosmic symphony with all these different particles being played out on vibrating strings. Now, I think our sources mentioned another approach to unifying quantum mechanics and gravity called loop quantum gravity, right?
Yes, that's another really interesting one. And it also gives spin a central role. Loop quantum gravity proposes that space-time itself isn't smooth and continuous like we perceive it, but it's actually made up of these tiny, interconnected loops.
Wait, so space and time are made up of loops.
That's the idea, and these loops are described by something called spin networks, which are these mathematical structures that encode the quantum state of space-time.
So in this theory, spin isn't just a property of particles, but it's a fundamental aspect of space-time itself.
Exactly. It paints a very different picture of reality than what we're used to, but it's a very compelling one.
So from these tiny particles all the way up to the vastness of the universe, spin seems to be this key that unlocks so many mysteries.
It really is, and the more we learn about it, the more we realize just how fundamental it is to our understanding of the universe.
Well, this has been an incredible journey.
We started by picturing a little electron spinning like a planet, and we ended up talking about the very fabric of reality. It just goes to show how much wonder and mystery there is in the universe.
And to think all of this came from exploring the spin of an electron. Thank you so much for taking us on this deep dive. It's been truly mind-blowing.
It's been my pleasure. And to our listener, I encourage you to never stop exploring and questioning. Who knows what other amazing discoveries await us in the quantum world?
Absolutely. Until next time, keep those minds spinning.